Today we're going to talk about the solution of homework 7. So let's look at the first problem. This is about a concept of chapter 5. So it says we have gas flows into and out of the chamber. And the problem is asking which of the following statements are true of the application of the control volume equation to the continuity principle. So first we look at this problem. We have a chamber here and we have a control surface and the control volume. So if we write down the continuity equation, it will be d over dt of the control volume rho times dv of the integral over the control volume plus the integral of the control surface, which is rho velocity times the area, which should be equal to 0. So this is our continuity principle. So that's when we look at this problem for part A, it says B system equals to 0, but we do have gas here, so it's not equals to 0. So the uppercase B system represents the generic property of the thing here. So in that case, we have similarly lowercase b, which is intensive property. It should be the B system divided by B, which is also not 0. So part A, selection A and E are both incorrect. And now we look at B because we have the continuity equation, so B is correct. And now we look at this part C. So actually mass in here will equals to rho A V, which will be given here 3 kilogram per cubic meter times, which area is 0.1 meter squared, times the velocity, which is 10 meter per second, and this will give us 3 kilogram per second. So that's the mass flowing. And now we look at the mass flowing out, which is rho AV as well. So for that case, we will have rho equals to 2 kilogram per cubic meter square, per cubic meter, times the area 0.2 meter squared, times the velocity 5 meter per second, which gives us 2 kilogram per second. So we could see sum of control surface B times rho A D equals to mass in minus mass out, which is per second minus 2 kilogram per second, which is 1 kilogram per second, which is not 0. Okay. here is not dA because it's the sum form. So selection C is not correct. And because we have the continuity equation, if this term is larger than 1, so this term should be smaller than 0. Okay. Therefore, part D is also not correct, which leaves us the only selection, which is selection B. Now we look at problem 5.48. So we have a tank here, and we have two pistons. One is called piston A, and it's moving at a speed which will be twice of the moving speed on piston B. So the problem is asking, in the tank, is the water level rising, not moving up or down, or it's falling? So we're gonna draw the picture here. So all the pistons are moving to the left. So we have a VA here, and we have VB here, and VA is equals to 2 VB. Okay, so we have a water, and we have the height of the water in the tank, and we have the area of the tank as well, and we will have a mass flowing out. We have a mass flowing in. Okay. So we're gonna use the continuity equation to solve the problem. Here we're gonna use the simplified form, which is d dt, mass of the control volume plus control surface, mass flow out, control surface of the mass flow in. It should be equals to 0, and let's move the control volume to the right. So the equation will be simplified to this term. Okay, so the mass flow is rho times V times A. So the rho's for the problem is the same. So rho V A times area of the A minus rho VB times the area B, which should be equals to d dt. And the mass of the control volume should be the area of tank times the height times rho. Okay. And we know the velocity of piston A is twice of the velocity of piston B. So be rho times 2 VB times the A, which is pi over 4 of the diameter, which is 3 inch square, minus rho VB times this has a piston B has a diameter of 6 inch. Okay, the entire thing here, because rho doesn't change and the area of the tank doesn't change, so it will be minus rho tank dH over dt. Okay. So we can cancel out all the rho here, and if we do the calculation, it will give us minus 14.14 VB, which equals to negative T times dH dt. So area of tank dH dt will be equals to 14.14 VB, and dH over dt will be 14.14 VB over AT. Okay. So of course the velocity VB is bigger than 0, therefore your dH over dt will be greater than 0. So the water in the tank is rising. Now let's look at problem 5.49. We have two streams discharged into a pipe, and we're given the QA and QB. Then we are asking to find the velocity at the acceleration of the fluid at the end of the exit at t equals to 1 second. So we are given QA equals to 0.01 t cubic meter per second, QB which is equals to 0.006 t to the power of 2 cubic meter per second. So both of the Q's are the equation of the T, so we can do the derivatives to find the accelerations using the equations here. So first we're gonna start with continuity equation, which Q in equals to Q out. So Q exit will be equals to QA plus QB. Okay, which will be 0.01 T plus 0.006 T squared. Okay. The first parameters we're gonna need to find is the velocity. So V exit equals to Q exit divided by the area of the exit. So the area is given 0.01 meter squared, so 0.01 T plus 0.006 T squared divided by 0.01 meter. So because the T is equals to 1 second, so I'm gonna plug in, and the answer will be 1.6 meter per second. The next step, we are going to find the acceleration. So acceleration will be equals to dEV over dt of the velocity, which is equals to partial derivative of v over partial derivative plus velocity times partial derivative of velocity over partial derivative of x. So because our velocity term here is the equation about t, so this term will cancel out. So only leave us the partial derivative v over partial derivative t. So acceleration will be equals to d over dt partial derivative 0.01 t plus 0.006 t squared over 0.01. Okay. And if we do the derivatives, it will give us 0.01 plus 0.006 times 2t. Okay. And we're asking to find answer at t equal to 1 second. So the acceleration will be equals to 2.2 meter per square second. Now let's look at 5.75. We have a tank with water here, and we have an outlet, and the velocity expression is given, and we are asking to find how long will it take the water surface in the tank drop from 3 meters to 0.5 meters. So we have the velocity equals to 2gh. We have the area of the outlet, which will be pi 0.03 squared, and area of the tank will be pi over 4 times 0.62 squared. So those are the basic information we have, and we're gonna use the continuity equation. Mass flow out is the mass flux flowing, which will equal to negative d over dt integral of rho times dv. Okay, because we don't have any water flow in, so this term will be cancelled, and we will only have the mass flowing out, which will be rho times area of the outlet and the velocity, which will equals to d dt rho dv. Okay. Notice we can cancel out the rho as well, so let's write down the equation again here. Area out times v will be equals to d dt over dv, and the dv can be written in the form of area of the tank times the height, because the height is changing with the time, so we cannot move the height out, but the area of the tank is a constant, so we can move it out from the integral. So equals to d dt times at integral of dh. And now we're gonna change the d over dt to delta t and move it to the right hand. We will get a out times v times delta t, which will equals to negative at times the integral of dh. Okay, now we're gonna plug in the expressions of velocity areas into the continuity equation here. We will get pi over 4.03 to the power of 2 times the velocity, which is 2gh, times delta t, which equals to negative pi over 4, 0.6 to the power of 2 times the integral of dh. And the pi over 4 can be cancelled out, and if we move the 0.6 to the power of 2 to the right, and we will have 0.036 to the power of 2 equals to, sorry, we have delta t here, which will equals to negative integral of dh over square root of 2gh. We're moving the 2gh term to the right because it contains the h parameters. So when we do the integral, we need to move it to the right. And the integral is from h1 to h2, which h1 will be equals to 3 meters and h2 will be equals to 0.5 meters. Okay, now let's do the integral. 0.03. First we write down the equation on the left and do the integral here, which will give us negative 1/2 and 1/2 over 2 times 2g. And this is from h1 to h2. Okay, so I'm gonna keep simplify the equation, which will give us 3 and negative sign here times the entire thing, which will be h1 to h2 half minus h1 to 1/2 over 0.5 times 2g. Okay. And we have h1 equals to 3 meters and h2 equals to 0.5 meters. So the delta t will be 6 3 5 minus 3 g. Here we're gonna use 9.81. Okay, so the delta t will be close to 185.1 seconds. Problem 6.7. We have a balloon rocket is held in place by a force F. The pressure inside the balloon is 12 inch of H2O. the nozzle diameter is 0.4 centimeters and air density is 1.2 kilogram per cubic meters. We are asking to find the exit velocity and the force. And we have assumption that we're going to ignore the rotational of the flow, and flow is assumed to be inviscid. So this problem first, when we look at this problem, we have different units. So the first thing we're gonna do is convert the unit to the SI unit. So the nozzle diameter D is 0.4 centimeter, which is 0.004 meters. And the air density, rho air, is 1.2 kilogram per cubic meters. And the pressure, which is equals to 12 inch 2O. So that means the pressure is equals to, when you have water that's 12 inch high, then the pressure should equals to rho of the water times G times the height. So this will be equals to 1000 kilogram per cubic meter times 9.81 Newton per kilogram times the height, which is 12 times, I'm going to convert inch to meters. Okay. Which will give us newtons per meter squared. So now we find the pressure which is inside the balloon. Let's say this is 0.1 and this is 0.2. So we're gonna use the Bernoulli equation with the pressure to find the velocity of the nozzle here. So let's write down the Bernoulli's equation, which will be equals to P1 over gamma plus Z1 plus V1 to the power of 2 over 2G, which equals to P2 over gamma plus Z2 plus velocity squared over 2G. So because we don't have any water flowing inside the balloon, so this term is 0 and Z1 equals to Z2, so it can be cancelled out. And P2 is open to the air, so it's also 0, which will leave us only the P1 and the V2 terms. So V2 squared over 2G will be equals to P1 over gamma. Okay, so V2 will be equals to of 2G times P1 over gamma. And we know gamma equals to rho times G, so this term will be 2 times P1 over rho, which is the rho of air. And we already find the pressure and the density is given, so 2 times 2,890 Newton per meter squared over rho of the air, which is 1.2 kilogram per cubic meter. Okay, so our V2 will be equals to 70.6 meter per second. So we already find the velocity. The next step is to find the force. We're going to use the momentum equation in the x direction, which is the horizontal direction, to find the force. So let's write down the momentum equation. So the sum of force in x direction will be equals to the mass flow flowing out times the velocity minus the mass flow flows in times velocity. Okay, because we don't have any water flow in, so we will only have the mass flowing out term. So Fx will be equals to the times the velocity flowing out, which is equals to the velocity too. So Fx will be times A times V2 squared, which will be equals to 1.2 kilogram cubic meter times the area, which is pi over 4 times 0.004 squared times the velocity, 70.6 meter per second squared. So the force is equals to 0.0751 Newton. Now let's look at the last problem, 6.13. A horizontal water jet at 70 Fahrenheit issues from a circular orifice in a large tank. The jet strikes a vertical plate that's normal to the axis of the jet. A force of 600 pounds is needed to hold the plate in place against the action of the jet. If the pressure in the tank is 25 psig at point A, what is the diameter of the jet just downstream of the orifice? So we have a point A here. We're gonna put our point B at the orifice, which is, you also can call it outlet. And the pressure here is 25 psig, and we have a force that's horizontal to the plate. F equals to 600 lbf. So first, for this problem, first we're gonna use the pressure and the Bernoulli's equation to find the velocity outcome from the orifice, which is point B, and then we're gonna use the force given here with the momentum equation and find the diameters of the jet. Okay, so now let's write down the Bernoulli's equation. PA over gamma plus ZA plus VA squared over 2G, which equals to PB over gamma plus CB plus VB squared over 2G. So both point A and point B is at the same elevation, so this term will cancel out. Point B is open to the air, so it's also 0. And point A don't have any velocity, so this term is also cancelled out. So this will give us only PA over gamma equals to B squared over 2G. Okay. So if we simplify that, we can get VB equals to square root of 2 times PA over rho. Okay. And we have the PA and we have the rho here, so VB will be equals to 2 times, notice the unit is PSIG, so we're going to convert that to the feet. Inch squared or feet squared. Okay. And over the density of the water is 0.94 feet squared. So our velocity will be 60.2 feet per second. Now we're gonna use the momentum equation. So the momentum equation will be sum of force in x direction equals to the sum of the mass flowing out, velocity, and minus the mass in times velocity. Okay. And when we look at the control volume control surface here, we can see we only have the mass flowing in x direction. Okay, so it's like here, flowing in here. So the equation be simplified to active mi times vi. Okay, and this will equals to active show b squared. Okay, and because the force is to the left, so the force here is negative 600 lbf equals negative rho, which is 1.94 per cubic feet, and times the area times the VB, which is calculated 60.92 feet per second. So the area will equals to 0.0833 feet squared. And the diameter is equals to A divided by the pi over 4, which will equals to square root of 4 times 0.0833 feet over pi, which will be 0.6326 feet.